This video is on differential equations specifically on growth and decay. So this lesson teaches us how to use exponential functions to model growth and decay in applied problems. Anytime you see some form of this statement, the rate of change of some quantity y is directly proportional to y, you automatically have to think of this. dy over dt is equal to ky. But not only that, if we were to take the integral of this and solve for it, which we will do in example 1, you end up using this function here. Y is equal to ce to the kt, where c is the initial value and k is your proportionality constant. If k is greater than 0, then you have an exponential growth. If you have k less than 0, then you have exponential decay. So now, doing example 1, we're going to prove that dy over dt equal to ky supports that the model will equal to y is equal to ce to the kt. So what we're going to do first is we're going to have our y's together. So we're going to divide by y and then send the dt to the other side. Now we're going to integrate, so then this is 1 over y dy, which is the same as ln of y, equals, k is just a constant, then you have the integral of dt, which is then t plus c. To get rid of ln of y, we would raise everything to the e. E and ln are inverses of each other, so they cancel out. Here, we end up with c e to the kt. Now let me explain how we went from here to here. In this portion right here, we have e to the kt plus c. Rules of exponents, we can split that up into e to the kt times e to the c. Well, e to the c is just a constant, so we can actually change that just to be to some value c. So then this becomes ce to the kt, which is what we have here. So let's do an example with actual values. So the rate of change of y is proportional to y. When t is 0, y is 3. When t is 2, y is 6. So what is the value of y when t is 3? Well, because of this statement right here, the rate of change of y is proportional to y, we automatically know that it's going to give us dy over dt is equal to ky, which then gives us the equation y is equal to ce to the kt. So the first thing we have to do is find the value of c. So let's find c using t is equal to 0, y is equal to 3. So 3 equals ce to the k times 0. K times 0 is 0. Anything to the 0 power is 1. So c is equal to 3. So our equation becomes y equals 3e to the kt. Well, now we have to find the value of k using t equals 2, y equals 6. So 6 equals 3e to the 2k. Divide by 3. 2 is equal to e to the 2k. To get rid of e, we would ln both sides. So we have ln of 2 equals 2k. Divide by 2, divide by 2. So k is equal to ln of 2 divided by 2. I'm starting to run out of space, so I'm going to change the color so you can follow along with the steps. Step 3 is to set up our model. So y is equal to 3e, k is ln of 2 over 2 times t. And our last step is to find the value of y when t is 3. So y is equal to 3e to the ln of 2 divided by 2 times 3. At this point, you would substitute this into the calculator, which would give you an approximate value of 8.48595. Let's look at another example. The number of bacteria in a culture is growing at a rate of 3,000 e to the 2t divided by 5 per unit of time t. At t equal to 0, the number of bacteria present was 7,500. That's going to be important. So find the number present at t equal to 5. Well, given that we have a rate that's being exponential, we know that we're going to use the model y is equal to ce to the kt. We know that when time is 0, the number of bacteria was 7,000. So if we were to substitute in 7,000 for y and t for 0, 7,500 for y, and let me rephrase that. This is our initial value right here. So we don't have to search for y we don't have to search for c because we're already given c. So it's y is equal to 7,500 e to the kt. So now, when t is 5, they want us to find the number of bacteria present, so they want us to find y. All we need to do is substitute in our values. E this should have been (2t) divided by 5. 2 times 5 divided by 5. Substitute this into the calculator and you get 55,417.92, which will round off to 55,418. So for our next example, a slow economy caused a company's annual revenue to drop from 530,000 in 2008 to 386,000 in 2010. If the revenue is following an exponential pattern of decline, what is the expected revenue for 2013? So I've already set up for our initial time back in 2008 as time is equal to 0. So when time is 0, we have a revenue of 530,000. In 2010, that would mean time is 2. We'd have 368,000. And we're looking for when time is 5, which is in 2013, we're looking for a revenue value there. Well, because it's an exponential pattern, then that's going to follow y is equal to the CEKT. We already have our initial value, meaning our C, which is this value here. So we have y equals 530,000 e to the kt. So using this, we're now going to find the value of k. So we're going to take our second point that was given to us. So 386,000 equal to 530,000 e. Okay. E to the 2t, or 2k, my bad. And we're solving for k. So divide by 530,000. Then we're going to take the ln of this value. I simplified it a bit. Equal to the 2k divide by 2 divide by 2. So k is equal to the ln of 386 divided by 530, the entire thing divided by 2. Okay, so I had to erase some stuff in order to make space. So ln of 386 divided by 530, the entire thing divided by 2 is approximately negative 0.159. So my model equation is y equals 530,000 e to the negative 0.159 t. Well, I'm going to use that, substitute in 5 for t to find y. So y is equal to 530,000 e to the negative 0.159 times 5, substituting into the calculator would give us a value of 239,913 with 16 cents.